Okay, in this video, we'll be going through the 2021 Scholarship Physics exam. Okay, question 1, neutrons. In this question, we have just a scenario where we have a nuclear reaction, and we need to use the concept of binding energy to explain why, in particular, a fission reaction occurs. Okay, so binding energy is the amount of energy required to separate a nucleus into its constituent nucleons. And so binding energy increases with nucleus size. So the bigger the nucleus, the harder it is to separate that nucleus apart. However, binding energy per nucleon is the average amount of energy needed to remove a nucleon from the nucleus. So as uranium has a lower binding energy per nucleon than its products, and we know that from like this graph right here, I'm sure you've seen it before. We have binding energy per nucleon, and we have a mass number over here. And so we see like a graph like this, and then there's like some jagged lines, but then ultimately it goes up here, and then it slightly drops off. And so iron is at the peak right here, so that's Fe. And as we get to more massive elements, so elements with a higher mass number, like uranium, we can see that the binding energy per nucleon is actually less than Fe. So even though binding energy is greater in uranium, the binding energy per nucleon is reduced. So as uranium has a lower binding energy per nucleon than its products are more stable. Thus, fission occurs because uranium releases energy as it breaks apart, and the products have a higher binding energy per nucleon. Thus, they're more stable. Thus, in other words, a fission reaction is an energetically favorable process. Example of this would be, you could say, a coffee mug, where the heat in the coffee wants to come out of the coffee and making the coffee having a lower energy state than it was previously. So particles such as neutrons also behave as if they have a wavelength, given by that equation there, where h is Planck's constant and p is the momentum of the particle. Show that the wavelength of the slow neutron with a kinetic energy of 0.04 electron volts is 1.43 times 10 to the negative 10 meters. Okay, so we're given kinetic energy, so Ek is equal to half mv squared, where our Ek is equal to our 0.04 electron volts, and we can get that in joules by timesing it by the charge of an electron, which is 1.6 times 10 to the 19, and we get 6.4 times 10 to the 21 joules. So that's our Ek in joules, because we can't use electron volts for this equation. Okay, so we can rearrange this equation to get the velocity of the neutron, so that's v is equal to square root 2 Ek over its mass, and so the v is equal to square root 2 times 6.4 times 10 to the negative 21, and that's all over the mass of a neutron, which is 1.67 times 10 to the negative 27, and that's given as 2769 meters per second. Okay, so as momentum is mass times velocity, we can substitute the mass of a neutron again, so that's 1.67 times 10 to the negative 27, times the velocity, which we just found, 2769, and the momentum of the neutron is equal to 4.62 times 10 to the 24, and that's kgs, meters per second. Okay, sweet as. So now we have Planck's constant, because it's a constant and we're always given it, and now we have the momentum, so now we can calculate the wavelength, which is what we're trying to find. So our wavelength is equal to Planck's constant over the momentum, and Planck's constant is 6.63 times 10 to the negative 34, I believe. Yep. And that's all over 4.62 times 10 to the 24. And that is indeed 1.43 times 10 to the negative 10 meters. And I believe that's what we're trying to find. Yes, sir. So in this scenario, we have two waves coming in and hitting crystalline copper. So we have the first wave hitting the first row of atoms here, and that second wave hits the second row of atoms. And so this concept is unfamiliar if you're just taking level 3, but what isn't unfamiliar is the concept of d sine theta. And so we know d sine theta is actually just our path difference. right? And we've obviously seen this in our interference pattern type of equations in standard level 3 waves. So this question is saying by considering the path difference, so we're definitely on the right track in terms of d sine theta, and show that the diffraction peak can be observed at angles 90 degrees. And so diffraction peak is probably a term that we haven't seen in level 3, but what that's saying is if we just consider a regular interference pattern, we have points of maxima scattered. Let's say we're shining red light, and we have points of maxima just like this, evenly spread. And so this is, we can see through a diffraction grating, shining red light through onto a screen, we get these points of maxima. Now, if we graph this, we can actually see this as little peaks like this, where every set of maxima is slightly higher than the last, with the middle one being the most intense. Yeah, that kind of fell off at the end, but you get the point. These are the same size, and these should be the same size as well. So we have the middle one being the most intense, because that's the brightest. But what it means by diffraction peak is basically these peaks. So we can see peaks like that. And so from that, we can interpret that a diffraction peak is just another word of saying maxima. This is just saying maxima. And to get a maximum, we normally say we need a whole number of wavelengths, and that is equal to our d sine theta, right? However, in this case, we need to be careful because these two waves right here have a path difference of 2 d sine theta, because we have a path difference of 1 d sine theta here and another d sine theta here. So in fact, we actually have 2 d sine theta as our equation. And from there, we can just rearrange for theta. So we get the inverse sine is equal to n lambda over 2d, and that's equal to our theta. And so plugging in our numbers, we get n, which will be, n in this case will be 1. We could say that's our maximum. And so 1 times anything is just itself, so we can get rid of that in our equation. Our wavelength is the wavelength that we just calculated in the previous calculation, so that's 1.43 times 10 to the negative 10. And that's all over 2 times our d, which is given up here. So 2.2 times 10 to the negative 10 as well. And that is equal to 18.96 degrees, or 19 degrees, rounded. So yeah, in this question, we're actually just talking about a neutron that is traveling this way at velocity v, and the path that it would travel would be like that of like a projectile motion, so like that. And what it's asking us is to calculate the vertical deflection, so basically this height right here. And so a way we can think about this is if we just drop that neutron straight down without throwing it, or, well, in this case, you can't throw a neutron, but you get the idea. It's going in a projectile motion. So if we just drop that neutron straight down, that height will be the same. So if the neutron followed this path rather than this path, this height will remain the same no matter what. And so from that, we can gather that we can use our formula d is equal to vt plus half at squared. So as it's being moved from a standstill, we can say that vi is equal to 0. Thus we can cancel this out, so d is equal to half at squared. And in this case, our acceleration is just g, right? Gravity, so 9.81, I believe. Does it tell us? Yep, acceleration due to gravity, 9.81 meters per second. But we don't have our time. So we can calculate our time using our trusty old velocity is distance over time. And so our time is our distance over our velocity, as this is our horizontal distance. So we got, that's 100 meters divided by our velocity, which we calculated up here, somewhere. Oh yep, right here. 2769, and our time is 0.036 seconds. So plugging that into here, we get distance is half 9.81 times 0.036 squared. And that gives us a distance of 6.4 times 10 to the negative 3 meters. There we go. So explain whether or not a uniform electric field can be used to compensate for the effect of gravity on the neutron. So if we have an electron and it's moving this way at a velocity v, because electrons have mass, it will be affected by gravity and the path it will take will be that of a projectile, just like above here. But we can use an electric field to compensate for this. So a correctly calibrated electric field, we can have a positive charge up here, and we could have a negative charge over here. So it will be repulsed by this negative charge and attracted to this positive charge. And what you can see is if the electric field is uniform and calibrated correctly, the electron can fly straight through, because the two forces are working together to keep the electron in the middle. However, as a neutron does not have charge, this wouldn't work because it will neither be attracted to the positive or repulsed by the negative. And so we can back this up using our equation F is equal to E over Q. As there's no charge, there'll be no force. So we can say nope, there will be no effect as neutron has no charge due to F is equal to E over Q. The electric field would have no effect on its path. There we go. So a typical guitar has 6 strings. 2 of these strings are tuned at notes A and D. When tuned correctly, the A string has a fundamental frequency of 110 Hz, and the 4th harmonic of the A string has the same frequency as the 3rd harmonic of the D string. So explain how the principle of beats can be used to determine if the D string is at the correct frequency if it is known that the A string is already at the correct fundamental frequency of 110 Hz. So we know beats is the phenomenon where we have 2 similar frequencies that superimpose, and due to the slight differences in their frequency, the 2 waves will come in and out of phase if you observe it from a single position. And so that gives the effect of beating, because when they come in phase, they superimpose and constructively interfere, loud spot, destructively when they're out of phase, quiet spot, so those creates a beating sound. So if beats occur when the 2 frequencies are slightly different, beats will not occur when the frequencies are the same. So if we know that the 4th harmonic of the A string has the same frequency as the 3rd harmonic of the D string, if the A string is played at the 4th harmonic, then we know that the D string is tuned correctly if we play the D string at the 3rd harmonic and no beats can be heard. So let's write that in. So if the D string is played at the 3rd harmonic while the A string is played at the 4th harmonic, no beats will be heard as they are at the same frequency. But if beats can be heard, then the D string is at the wrong frequency and is not tuned correctly. So calculate the fundamental frequency of the D string when it is tuned correctly. So we know that the 4th harmonic of the A string is equal to the 3rd harmonic of the D string. The 4th harmonic of A is equal to 440 hertz. 440 hertz, there we go. And so we can substitute that in. So 440 is equal to the 3rd harmonic of the D string. And to find the fundamental frequency of the D string, we can divide it by 3. So 440 divided by 3 is equal to the fundamental frequency of the D string. And that is equal to 146.67 hertz. There we go. So some guitars use a set of 3 identical springs to apply tension to the strings. The 3 springs all have a constant spring constant of K and an unstretched length of L0. They're then stretched and connected between the bottom side of the pivoted metal plate called the bridge and a fixed metal plate as shown. Show that the net force applied onto the bridge by the connected 3 stretched springs is given by that equation there. So we know the equation when we have a force applied to a string is equal to F is equal to Kx. we ignore the negative here because we're not worried about direction in this case. So in this equation here, x is our length that we stretch. So if we read the equation, we know that L naught is equal to unstretched, and L is equal to the stretch length. And so x is the difference between the two. So what we're actually looking for is when we have our unstretched and we stretch it a little bit, we're looking for the x is that distance here. So if we have a spring, this will be our unstretched length, will be L naught. And if we stretch the string, it will gain an extra distance, which this distance here is our L. The x what we're looking for is this. And so from there, we can say that our x is equal to our L minus L naught. So for our first equation, we can say F is equal to the spring constant times L minus L naught, like this. So this is for the middle spring. And the reason why this is only for the middle spring is because we can see that these other outer strings are at an angle. So we have to take into consideration that theta right there. So the middle one is the only one that goes straight. So that is the equation for our middle string. However, our outer spring, we only need to calculate one outer spring because the other ones are identical. So if we find the force on one, we can just multiply by 2 and we get the other one. And so for our outer spring, as it is at an angle like we discussed before, it's going to be stretched slightly longer than the middle spring. And to find out how much it's been stretched, we can go to our trusty trigonometry and we can draw a little trusty triangle on here. Let's draw, let's use a like this, and like that, and like this. That's a right angle, and we have our theta there. So this base length right here is our L, as it's already been labeled for us. And this, similar to our depiction, this is our L naught plus x. And so we can see using trigonometry, this is equal to cos theta is equal to L over L naught plus our x. And so rearranging this for our x, we can get L naught plus x is equal to L over cos theta, and x is equal to L over cos theta minus L naught. We can sub that into our f is equal to kx, so f is equal to k L over cos theta minus L naught. However, this equation here accounts for both the horizontal and vertical components, so it's the total force. However, in this case, the vertical components of the force are going to be opposing each other, and so they cancel out. And so the equation only accounts for the horizontal component of this force. And to get the horizontal component, we can times everything by cos theta. So L over cos theta minus L naught cos theta. And so expanding this out, we get f is equal to k L minus L naught cos theta. And so combining everything together, we combine the middle spring and the outer springs together, so we get f is equal to the middle spring, which is k L minus L naught, plus 2, because again we have 2 outer springs, so we times this equation by 2. So 2 k L minus L naught cos theta. Expanding everything out, we get KL minus KL naught plus 2KL minus 2KL naught cos theta. Gathering our like terms, we can say that f is equal to 3KL, and we can see that KL naught is a like term in these two equations here. So we can say minus KL naught 1 plus 2 cos theta. And finally, taking out k as a like term, we can say that f is equal to k 3L minus L naught 1 plus 2 cos theta. And that is the final equation that we're trying to find. And so for this question, again, we need to derive a absolutely horrendous, horrific, heinous formula. That is that. And so there's a few things going on here. One, there are forces being applied away from the pivot, so that implies torques. So we have a force on the strings, which we just came up with before, so that's that. And so we can say that the T is equal to force times distance, where the torque of the spring is equal to this force right here, which I'm just going to label F0, because I can't be bothered writing out the whole thing every single time. So that is equal to K3L minus L0, 1 plus 2 cos theta. And so the tensions on the spring is equal to F0 times D2. Now there's going to be another torque provided by the strings. And so this is going to be T string, the force from the strings, and that's going to be the tension force from the strings. As there are 6 strings, that is 6 times the tension force, and applied over the distance D1. Therefore, as we know, our torques have to be equal. So the torques from the spring is equal to the torques from the string. And so F0 D2 is equal to our 6T D1. So now from here we can solve for tension force by dividing both sides by 6D1, and we get F0 D2 is over 6D1 is equal to our tension force. Okay, so now that we have that, we can put that to one side. So we have an equation here where we now have our tension force, which is right here, but we don't have frequency in this equation, but there's a frequency right there. So how do we add frequency? Our most obvious way in would be V is equal to F lambda. So we can say that F lambda is equal to the square root T over mu. But now we can run into another problem. We don't have lambda. However, we're given a clue that we are trying to find the fundamental frequency of the string. And so if we have a string, 2 nodes on either side, we know that there is going to be a antinode in the middle. And this length right here is equal to lambda over 2. And so our wavelength is equal to 2 times the length. Our length is given by z, so lambda is equal to 2z. So plugging that in here, we get 2zf is equal to square root t over mu. Plugging in our tension force, we get 2zf is equal to the square root of F0 D2 all over 6D1 mu. Now squaring both sides to get rid of that square root, we get 4z squared f squared is equal to F0 D2 all over 6D1 mu. Now we can rearrange for frequency, and we get f is equal to the square root of F0 D2 all over our 4 times 6, which is just 24, z squared D1, and then finally our mu. Finally, plugging in our F0, we get f is equal to the square root of k D2 3L minus L0 1 plus 2 cos theta all over 24 mu d1 z squared. And that right there is our final equation. Okay, so in this scenario, the D string snaps, and we need to explain how the fundamental frequency on the A string will be affected. So first of all, if the length is constant, we know that wavelength is directly proportional to the length, so in this case z. So if z is constant, then we can say that lambda is constant as well. And also because the length is constant, we know that the linear density, which is a mu, will also be constant. So therefore, mu is constant also. right? So taking our equation above, we know the velocity is equal to the tension force over the linear density. And as v equals f lambda, we can say that f lambda is equal to this equation right here. Right, we know that lambda is constant and we know that mu is constant. So what we're only worried about is the frequency and the tension. So we can say that the frequency is directly proportional to the square root of the tension force. So we know that one of the strings snaps. So the tension force goes from 6t to 5t. So the force initially was 6t. Now the force finally is 5t. So that means rearranging for t, we get over 6 is equal to t, whereas f over 5 is equal to t. We can take the proportion of this increase in our tension force by taking the final divided by the initial. And these forces will cancel out, giving us 1 over 5 divided by 1 over 6. Which is equal to 6 over 5. That is the proportion of increase of our tension force. And so if our tension force increases by 6 over 5, that means our frequency has to increase by the square root of 6 over 5. And so we can take the fundamental frequency of the A string, which was, I'm sure, given up here somewhere, 110 Hertz. And we can take the square root of 6 over 5 times 110 Hertz to give us the new frequency, and that's equal to 120.5 Hertz, and that's our new frequency. There we go. Okay, question 3, about a ball. A ball with a mass m is launched at a speed v at angle theta. The projectile lands at the same height that it was launched from. Okay. So by considering the components of velocity, blah, 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 show that the distance traveled is v squared over g. So as we are talking about horizontal distance, we can say that v is equal to distance over time. The question gives us a clue by considering the components of velocity. So if we draw out this situation here, we have theta here. This is our v, pointing this way. So therefore the horizontal component would be v cos theta, as we have a hypotenuse and this is our adjacent side. Therefore the vertical component right here would be v sine theta, right? So taking that into account, as this is for horizontal distances, this would be v cos theta is equal to distance over time. And so our distance will be v cos theta times time. Now, we need to find a equation for time, because we do not have time in this equation right above. So we can use the kinematic equation v final is equal to v initial plus at. So rearranging this equation for time, we get t is equal to vf minus vi all over our acceleration. Now, as this kinematic is dealing with velocity in the vertical direction, we will use our vertical component of our velocity. Now, in defining some definitions for our vf and vi, we can say that our vf will be negative and our vi will be positive. The reason for this is because the projectile lands at the same height that it was launched from. Therefore, initially, the projectile will be going upwards, and so we can define this direction as positive. And finally, at our vf, the projectile will be going downwards, and so that we can define that direction as negative. And so we get t is equal to negative v sine theta minus v sine theta all over our acceleration, and our acceleration in this case is just g. And we do not have, and as you can see, I have not labeled vf and vi at the top because they will have the exact same magnitude, because again, the projectile lands at the same height that it was launched from, so the velocity in the beginning will be the same as the velocity at the end, just again flipped due to the vector. And also g is negative in this case because g is going downwards. So we can say that this is equal to negative 2v sine theta all over negative g, and so we can take out the negatives because it's negative on both the top and bottom, so we get 2v sine theta all over g. Now subbing this into here, we get d is equal to v cos theta 2v sine theta all over g. Now this little trig identity is given to us and it comes in very handy. As you can see, this is seen right here. As we have our cos and our 2 sine theta right here, we can simplify this as v squared. Again, we get our v squared from timesing this v with this v. And this is sine 2 theta all over g. Now our launch angle is 45 degrees, so 2 times theta would be 2 times 45, and that's equal to 90 degrees. And sine 90, as we know, is equal to 1. So that means d is equal to v squared times 1 all over g, and so d is equal to v squared over g. And that is our final equation that we're looking for. There we go. In this situation, we have a drag force acting on the ball. An assumption that has been made is that the drag force is constant and only in the horizontal direction. So now we need to prove that the distance traveled by the ball will be given by this equation here. So for this equation, we can use the kinematic equation VIT plus half AT squared. Some modifications we can make to this is the acceleration in this case would be g. And as g is negative, we can change this sign to a negative, and we'll change this to g. There we go. Now our velocity initially will be vi will be v cos theta, as we're only worried about the horizontal component. So that would be v cos theta t minus half gt squared. Now our g we know is equal to F is equal to mg, therefore g is equal to our force over our mass. So we can make that substitution in, and we get v cos theta t minus half F over m t squared. Now from our previous question, we know t is equal to 2v sine theta over g, and so we can make that substitution again. We get v cos theta 2v sine theta all over g minus half F over m 2v sine theta g squared. Now simplifying this down, we get our v squared, and again we see our cos to sine theta over here, so we can say that this is sine to theta, again using this trig identity up here. And that is all over g minus 2f v squared sine squared theta all over our mg. Now our 2 is from this 2 being squared, so that will equal 4, and it's being halved over here, so we get 2. Our force is from here, and our v squared is from this being squared with this, and again same with our sine squared being squared with this. And that's all over our mg squared. And so we can simplify this by taking like terms. We have v squared g on both equations, so we can take that out as a like term. So we have v squared over g, and that's equal to sine 2 theta minus 2f over mg sine squared theta. And that is the equation that we have above. There we go. Okay, part C now. Discuss the validity of the assumptions made about the drag force in part B. Describe more realistic assumptions about the drag force and explain how these would affect the horizontal distance traveled by the ball. Okay, so one claim that we made about the drag force was that it acted only in the horizontal direction, and it's constant the entire time. However, we know that the drag force will act in direct opposition to the direction of the ball. So if the ball is moving in this horizontal direction, there will be a drag force going diagonally down the opposite way. So if the drag force is going diagonally down this way, then we can assume that there will be a horizontal component of this drag force, And there will also be a vertical component of this drag force. And so let's put this in words. So the drag force, dF, will act directly opposite to the direction of the ball's motion. Also, rather than a constant drag force, the drag force will increase as the velocity of the ball increases. Thus, there will be a larger downward acceleration due to the vertical component of the drag force. Thus, the max height will be reduced and therefore reducing the total flight time and horizontal distance traveled. However, as the horizontal velocity decreases, this will result in the horizontal component of the drag force to decrease, compared to a constant drag force. Thus, this may result in a change in the total range. The reason why we say change rather than increase or decrease is because there is sort of conflicting elements here. We are saying that the horizontal distance is decreased, right? However, if the drag force decreases in the horizontal direction, this may cause an increase in the horizontal distance traveled. So there may be either a decrease or an increase depending on whether this is more significant or this is more significant. And so that's why we say change rather than increase or decrease. And so this second part is pretty tricky. So what's actually happening is as the ball moves faster, the drag force will increase. Therefore, as the drag force increases, this will cause the horizontal velocity to decrease, but because the size of the drag force is dependent on the velocity, if velocity decreases, then the drag force in the horizontal direction will decrease. And so that's the trick to understand this second part right here. Okay, after receiving an initial push, the solid ball begins to roll up a slope as shown on the right. The ball has a mass m, radius r, and the moment of inertia is 205 mr squared. When it is at height 0, the center of mass of the ball has a velocity vi. When it has reached a height h, the center of mass of the ball has a velocity of v. So show that the velocity of the center of mass of the ball v when it has reached height h is given by that equation there. So this is a problem of conservation of energy. So our energy initially is equal to our kinetic energy initially, which is mvi squared, right? Because when it has a height of 0, the ball has a velocity of vi, and also our rotational kinetic energy, which is half I omega initially squared. And so we know that our angular velocity is our velocity over our radius. And so in this case, our omega I is equal to our velocity initially divided by our big R, because that is our radius given. And so omega I squared will be equal to vi squared over r squared. And so we can make that substitution equal to half mvi squared plus half I in this case is given to us right here. So that is 2 over 5 mr squared all over vi squared over r squared. Now these two r's cancel out and we are left with energy initially is equal to half mvi squared plus 1 over 2 times 2 over 5 is equal to 1 over 5, and we have mvi squared. And adding these two together, we get 7 over 10 mvi squared as our initial energy. So as we know conservation of energy, we know that our energy initially is equal to our energy finally. So our final energy is equal to our kinetic energy, linear kinetic energy, and this will just be v, because when it has reached height h, the center of mass has a ball velocity of v, so it's just v squared, plus our half I omega squared. And then also, because now we're at the top of the slope, we have some gravitational potential energy. So we have our mgh. So we know that this section here is just equal to this, because that is what we had over here. And so we can rewrite this as EF is equal to 7 over 10 mv squared plus mgh, and that is our energy finally. So our energy initially is equal to our energy finally. So 7 over 10 mvi squared is equal to 7 over 10 mv squared plus mgh. Taking out our mass as a like term, we can say 7 over 10 mvi squared is equal to m 7 over 10 v squared plus GH. Now we can cancel out these m's, and we get 7 over 10 Vi squared is equal to 7 over 10 V squared plus GH. Now we are trying to find our V velocity, so we're trying to find this, so we can rearrange for that. And so we can move our GH onto this side, and we get 7 over 10 Vi squared minus GH is equal to 7 over 10 V squared. Dividing both sides by 7 over 10, we get 7 over 10 Vi squared minus GH all over 7 over 10 is equal to our V squared. Now we can split this up, and so we got 7 over 10 Vi squared all over 7 over 10 minus GH all over 7 over 10. We can now cancel these two 7 over 10s, and we get Vi squared minus GH 7 over 10 is equal to our V squared. Now simplifying this, we can get Vi squared minus 10GH all over 7 is equal to our V squared, and then square rooting both sides, we get the square root of Vi squared minus 10GH all over 7 is equal to our V, and that is the final equation that we are trying to find. So give an expression for the maximum height reached by the ball when as it rolls up the ramp. So we know that max height when V is equal to 0. And the reason why that is because if you imagine as it reaches the top, momentarily it comes to a complete stop before rolling back down. And so that's how we know that velocity is equal to 0 when max height is reached. So we have our equation for our velocity, which we just found out, which is Vi squared minus 10GH all over 7. And so when that is equal to 0, we got the square root of Vi squared minus 10GH all over 7. We can square both sides to get rid of that square root, and we get 0 is equal to Vi squared minus 10GH all over 7. Moving this to the side, we get 10GH over 7 is equal to Vi squared. And now rearranging for H, we get H is equal to 7Vi squared all over 10G. And that is our final expression. Question 4 now. A parallel circuit is connected to a 110 volt DC supply and a switch as shown. One branch is connected to the 22.4 ohm resistor, which is labeled R1, and an uncharged capacitor, C, in series, and the other branch only has a 27.5 ohm resistor, which is R2. Sketch clearly labeled lines/curves on the axis on the right to show how the voltages across R1, R2, and the capacitor will change when the switch is closed after t is equal to 0 seconds, and explain why the voltage across each component changes this way. So we know when the switch is closed, the capacitor will allow free-flowing current, so max current will reach as soon as the switch is closed, but as the capacitor gets more and more charged, due to charge building up on the capacitor plates due to repulsive forces, it will become harder and harder for the charge to accumulate onto the plates. Thus, the current will slow and eventually come to basically almost 0. However, because this is a parallel circuit, this will only affect this branch. R2 will receive the full 110 volts the entire time. And so let's write that in. So as R2 is in parallel with the supply, it receives a constant 110 volts, so it's unaffected by the capacitor gaining charge. However, as the capacitor is initially uncharged, the potential difference between the two plates is 0, thus the voltage will be 0. However, as the capacitor, that's not how you spell capacitor. However, as the capacitor accumulates charge, the voltage across the capacitor will increase until it is fully charged. At this point, the voltage across the capacitor will be 110 volts. As R1 is in series with the capacitor, it initially has a voltage of 110 volts, as the current is only limited by the resistance of R1 in that branch, right? When the capacitor is uncharged, current can just flow straight through, and so the only resistance for the current is the resistance of R1 in that branch. However, as the voltage across the capacitor increases, the current through that branch will decrease, right? Because the capacitor will gain some more charge, and therefore repulsive forces will prevent that current from flowing. And this will continue until the voltage across R1 is 0, when no more current is able to flow through that branch. Drawing this out in our graph, we get R2 will receive a constant 110 volts, so that will be R2. Our capacitor will increase in voltage over time, so it'll go like something like this. And that's our capacitor. And finally, R1 will be the inverse of our capacitor, so it'll be like that. That's kind of trash. That's good enough. That's R1. You get the idea. So the capacitor is removed from the circuit and replaced with a non-ideal inductor. The non-ideal inductor has both inductance and an internal resistance of R. At t is equal to 0, the switch is closed, and the voltage on each component R1, R2, and L is measured for 3 seconds and plotted against the graph, as you can see there. Using physics principles, explain why each of these 3 lines on the graph has the shape that it does. Okay, so R2 is in parallel with the supply, so it receives a constant 110 volts, just like in the previous question. As there is a high rate of change in current, there will be a high rate of change in flux, thus there will be a high back EMF. This back EMF is equal to the supply voltage of 110 volts, and will impose oncoming current. However, over time, the rate of change of current will decrease, and thus the back EMF will also decrease. Thus the current will increase. This will continue until current is steady and constant. At this point, the voltage across the inductor will be 10 volts, and I got that value from simply looking at the graph. You see 10 volts here, and that is where the... That is where the inductor rests at the end of the 3 seconds. As R1 is in series with the inductor, the voltage across the inductor and R1 must add to 110 volts because voltages in series add together. Thus, in the beginning, when the switch is initially closed, the voltage across R1 has to equal 0 volts because when the switch is initially closed, the voltage across the inductor is 110. So 110 plus 0 is 110. However, as the voltage across L decreases to 110 volts, the voltage across R1 will increase to 100 volts, which is right here. So 100 plus 10 is 110. And so use the information on the graph above to estimate the time in which the current through R1 is equal to the current through R2. And so from this equation, we can form an equation where the current through 1 is equal to the current through R2. As V equals IR, we can rewrite this equation as V1 over R1 is equal to V2 over R2. Now, reading from the above, we know that the voltage across R2 will be a constant 110, and we have the resistance of R2 and the resistance of R1. So we can plug that in. We don't know our V1 because our V1 constantly changes, as we see here. So we have our 22.4, that is our resistance across R1, and that's equal to 110 divided by our 27.5, which is our resistance across R2. So, rearranging for V1, we get V1 is equal to 110 over 27.5 times 22.4. And so our V1 is equal to 89.6 volts. So when V1 is equal to 89.6 volts, that is when the current of R1 is equal to R2, and we can see this time by looking at our graph. 89, which is somewhat here, we can come directly down, and that's around 1.2 seconds. Using information from the graph, calculate the value of the inductance and the internal resistance R of the non-ideal inductor. So as we know, in a series circuit, so if we draw up a little mini series circuit where we have a resistance, and let's go like that, sweet as, we know in series that the current of this bulb must equal to the current of this resistor. So we can extrapolate that knowledge and say that in this branch we have a resistor R1 and an inductor in series, and so the current between R1 and the inductor must be equal. So R1 reaches a voltage of 100 volts and it has a resistance of 22.4. So we can use that information to calculate the current across R1. So that's 100 divided by 22.4, and that's equal to 4.46 amps. So as the current of R1 is equal to the current across the inductor, we know that the current across the inductor must also equal to 4.46 amps. And so now that we know the current across the inductor, we can figure out the resistance of the inductor. So we have the final voltage of the inductor, which is 10 volts, and that's all over the current, and that's equal to 2.24 ohms. So now we can use our equation T is equal to L over R, and we can rearrange this for L, and we get L is equal to T times R. Now to find out our time constant, we can figure out the time taken for R1 to increase its voltage by 63%, and thankfully this is very simple math. As the voltage of R1 plateaus at 10 volts, we know that a 63% increase of this will be at 63 volts. And so if we zoom in, 63 volts will be roughly here, and if we draw a line across and straight down, we get 0.5 seconds. And so our inductor is equal to 0.5 times the resistance. Now this resistance is the total resistance of the branch, so this is 2.24 plus the 22.4 of the R1, and so we get 2.24 plus 22.4, and so our inductance is equal to 12.32 henries. That's our final answer. Okay, and that will do it for the 2021 scholarship physics exam.